I'm pleased to be here and talk about an important aspect of this conference, which is wildlife research and how we can use wildlife research to understand impacts, and those impacts can then provide important mitigation steps. And I'm at the University of Wyoming, like was mentioned previously, and I wanted to point out some things about our state and energy development. It is the driving economic force in our state. We have other sectors such as agriculture and tourism. Tourism is also very important. But I think a lot of folks think about Wyoming as kind of the northwest section with a beautiful two large national parks, Grand Teton and Yellowstone Park, with geothermal features, abundant wildlife, and wonderful scenery. But we also have across the state a very large energy sector. One thing maybe not everyone's aware of, but we're the #1 coal producing state. We also produce more bentonite clay than any other state or region in the world. And oil and gas development is very featured within our region. Oil and gas development started in 1883, and currently we provide 1/8 of the production of gas for the United States. A little bit more about oil and gas development. By the end of 2011, there were 69,000 producing oil and gas wells. And just looking at the spatial context of this, as far as the boundaries of currently producing oil and gas well fields, almost 20% of the state has a boundary included within that region. And it was said earlier about Utah, $4.5 billion for all energy. Just the oil and gas sector is a $9 billion industry per year in the state of Wyoming. So there's other resources too. Earlier in the conference, there were a few kind of things that were said about how air masses move between states. And in my yard, actually, my tree has been to the east, so I don't know where Nebraska fits into this, but if you look across this, the High Plains region of the United States has the highest wind potential, and that wind potential is starting to be developed for wind energy. And just look back in time, 1999, you see that Wyoming did have some development, but as time progresses, that development has increased greatly until we're also one of the top wind energy producing states as well. So when we talk about energy development or any other kinds of development, there are definitely kind of two general sets of impacts that scientists study. One would be direct impacts. These tend to be a little bit more easy to get a handle of, like direct habitat loss and mortalities that could occur as a result of something going on in a development. Then there's this other type of impact, which is indirect impacts. And these are the types that tend to be examined and quantified through understanding avoidance behavior of wildlife. And then there's a set of things that go along with that are cumulative impacts that are related to fitness consequences like lower survival or nest success, or movements away from infrastructure that may lead to some issue in the migration ecology of the species and so forth. So today I'm going to talk mostly about indirect impacts. Quite a really interesting area of research. Quite a bit has been said here about the greater sage-grouse. They're really a focus. Probably one reason why is because they have been declining, but they also represent the health of the sagebrush ecosystem. And in our state in 2008, our governor at the time established a sage-grouse executive order where core regions were put in place, which then we're using some of the research that had been provided earlier to devise strategies for conservation of this species. And when you think about sage-grouse and the potential of them being an umbrella for other species, we have to think about what those species are. And I have a diagram here just showing some of the other species, including sage-grouse, that occur in the sagebrush steppe, but it's actually a fairly diverse system. There's about 100 avian species and about 70 or 80 mammal species that really depend on sagebrush, including some real charismatic species like mule deer and pronghorn. And now we're starting to understand that some of our other species, some of our game species like elk, also are impacted by energy development. And it's important to understand those relationships, as well as a really common species in sagebrush, the pronghorn, which I think we oftentimes think are quite able to handle or habituate to human disturbance. So I wanted to start off by talking about some work I've done this last year, looking at the spatial heterogeneity of male sage-grouse luck attendants across Wyoming. And I used some data provided by the Wyoming Game and Fish Department, which is, we extracted 815 Leks from their Lek database. And they have information on about 2,300 Leks that occur across the state. And we used 815 that met some criteria we needed to use in our modeling. And then adjacent to this diagram, you see these are actually the 69,000 well pads that I was talking about earlier. So you can see kind of that extent, right? There's a lot of those well pads out there. Then we converted those data into raster grid, and especially with the oil and gas well pad density, you looked at different scales across time, 5 different scales of analysis. And because this kind of data is really variable, there's a lot of spatial autocorrelation involved. We use a procedure called a graphically weighted regression, or GWR, to evaluate our data. And it provided a means for us to understand some of the relationships with well pad density and also time, since well pads are installed as a lag effect in Sage-Grouse Lek attendance. And what we found in this model was, first, that it provides a global model because it actually, the way that this GWR analysis works, it goes across the landscape, identifies different groups of Leks, in this case, that are spatially correlated, and then it does a regression. It takes parameter estimates from each one of those individual regressions and then makes a global model across all of them. We're able to explain with the global model 66% of the variation in male Lek attendance, which is really good for ecological data. And then probably our singular model that explained the most was 32% of the variance was explained with a 5-year window of time, which happened to occur from 2007 to 2011. And further identifying some of the individual model variates that were important, the predictor variables or covariates are important. We used a Monte-Carlo simulation. We found, just in this set of data that we have a 1-year and 4-year time lag effect that was very evident in our results, as well as development densities of well pad development within 1, 2, and 10 kilometers of Sage-Grouse Leks. So that gives us a lot of information already about trying to identify impacts and maybe what that means for mitigation later on. And then we look at this spatially displayed on these 2 diagrams. And the one on your left, right here, happens to be the 4-year time lag, and then the one on your right happens to be the 1-year time lag. And you see all those points on there. The green points represent stable to increasing Leks during 2007 and 2011. The red represent the decreasing Leks. And there's quite a bit of change there. That's the spatial heterogeneity, depending on the scale you're looking at. For instance, at the 10-kilometer scale and the 4-year time lag, you see this region down here in south central Wyoming, the Leks are decreasing. They're impacted at that scale within 10 kilometers, but at a smaller scale, 1 kilometer, that effect wasn't seen. So, we look at those results and try to understand better maybe what's going on. But overall, 80% of the Leks during 2007 to 2011 were declining, and 20% were either stable or increasing across the state. And we have to try to understand that now, just projecting the future with the ability for us to predict with our regression information into the future, the next 5 years. What you see with a stable to increasing is about a 3 mil per Lek per year increase that we predict will occur. And then with those that are decreasing, there's almost a double negative result of that at 5 or 6 mils per Lek decline. But what I want to point out, and I've circled these confidence intervals, the upper part of the 95% confidence interval includes the lower part for the decreasing in both situations, which indicates that there are some Leks out there that are persisting either stable or slightly increasing with the same well pad density as some of those Leks that are declining. And so it's important for us to understand the configuration of well pads and maybe how that influences this result. And so you look at this landscape right here. It is possible that in some areas some Leks will persist and maybe even increase a little bit, but we have to understand the configuration of well pads and how that may influence that. And Kevin Doherty in 2010 published this article, and they showed just graphically 11 Leks in the state where there were more than 40 well pads within a 3.2 kilometer distance around a Lek. And those little dark points are the Leks. The well pads. The Lek is in the center of the circle. And those Leks actually persisted. So we need to understand that a little bit better. So I show you this information here just to kind of pinpoint. We can learn a lot about impacts, but the impacts are also, it's necessary when we finally identify how they work, with the mechanisms that are causing those impacts. So I wanted to now talk about 3 case studies that me and my graduate students have been working on. And I've had at least a half a dozen of my graduate students that have worked specifically on energy development. And our study areas kind of go across the state of Wyoming. The study areas that are bolded in red are the 3 case studies I'm going to describe. The first is the elk study area in northeast Wyoming, Fortification Creek. 7 Mile Hill is a wind farm in Carbon County, Wyoming. And then the Atlantic Rim is an oil and gas sage-grouse study, also in Carbon County. So this is looking at Fortification Creek. It's a year-round habitat for elk, and it's about 123,000 acres in size. The BLM has been really interested in this area for quite some time. Those elk are non-migratory. They stay there year-round, and there has been some development for quite some time, but actually it really picked up in 2000, and we evaluated elk specifically from 2008 to 2010. By the end of our study period, there were 700 coal bed methane wells that are producing gas at that point. And future plans call for 80-acre spacing, which would be about 2,000 wells in this general area. So we had this study had something that was really nice that not all energy studies have, which is we had data before the impact occurred, which allows us to make some different inferences. And so we had pre-development data the Wyoming Game and Fish Department collected with VHF monitored elk. Then we had a sample of GPS elk that we studied from 2008 to 2010. Then a new sample of elk were equipped with GPS transmitters in early 2011, and now we have that information. We're using that for validation for our earlier data. And so this is what I'm going to show you now is a time series of resource selection functions. Now this is before the development occurred. At this time, what we know, the elk were being impacted by roads and elevation. That's what they responded to in this system, avoiding roads but selecting higher elevations. And then now this is our first year of during development. And then just start to watch as I go through a series of slides here how the well pads and then the road network is starting to increase. And that brown area is where the elk high probability of use is occurring. And so I go now to 2009, and I've still got elk that are occurring kind of across the landscape, including the southern area, in both summer and winter. And then by 2010, the summer indicates that elk have actually mostly left that southern area. So you do see a shift over time as the development increases. And so I had Clay, my graduate student, evaluate some mechanisms that might be causing elk to respond to the infrastructure. And one thing he did was measure traffic volume. And you see there's 3 kinds of roads that the BLM define. We have well roads, access roads, and main roads. And it's quite different as far as the traffic volume per day. But that's important to understand later. And then what I'm showing right here is actually a sound map. So Clay measured sound and modeled sound in the area. And the blue areas are ambient noise. And 85% of the locations in just this one year, in 2008, occurred in that blue area where it was quieter. Outside of the area, in kind of the red areas, that's about 38 decibels greater than ambient, and there's very few locations in there. So what did we learn about this study that might have implications for mitigation? From the before impact data till during 2008 and 2010, elk actually lost 30% of their high use area that they used before. And we also, Clay looked and remodeled his data. If he was able to reduce the traffic volume to what we found on the well roads, which is only 4 vehicles per day, that would actually reduce indirect habitat loss somewhere between 40 to 70%. And we also found a couple other things too. As the development occurred, there was a wilderness study area in that top northeast part of the area. Elk actually use that increasingly because of all the activity, and they also used more juniper in the study area as cover, hiding cover. So I'll talk about the first sage-grouse study. This now is part of the National Wind Coordinating Consortium, one of the replicated field sites for their effort to understand wind energy development in sage-grouse. And it occurs in Carbon County between the towns of Hanna and Medicine Bow. And PacifiCorp owns this wind farm, and they erected 79 1.5 megawatt wind turbines in 2008. And we studied these grouse starting in 2009, 2010. And what we found was we have a model that includes environmental and anthropogenic infrastructure variables, and we found that Sage-Grouse, both for nesting and brood rearing, responded negatively to the wind turbines, to distance to wind turbines. If you look at these hazard ratio diagrams here, what you see, especially for nests, is there's really a prolonged effect, quite a distance out, where they had lower nest success in relation to those turbines. And then with the brood rearing, with brood survival, that happened to fall off a lot sooner. Maybe after about 5 kilometers away, there wasn't much of an effect. But it does show that there is, in this case, some really strong effects from those wind turbines. Earlier models we did with occurrence modeling showed that the sage-grouse used this area repeatedly, but when the wind turbines were installed, it showed that they responded to it negatively. And this is just some of the distances. If we just look at 3 scales, 1 kilometer away, the rate of risk increases by almost 94%. At 3 kilometers, it drops down a little bit to 82.5, and then by 10 kilometers, still almost 53% greater risk of a nest failure near those turbines at 10 kilometers. Not quite a strong relationship with brood survival, but close by, about 62% when you're within 1 kilometer and 24% when you're outside of 3 kilometers. So this is the final sage-grouse case study I wanted to talk about. This occurred in the Atlantic Rim, which is a really productive area for sage-grouse. There's 89 Leks in this area, and this is also coal bed methane that's being developed here. The plans call for about 2,000 wells. The BLM record of decision allows for that many eventually. However, development has slowed down a lot since the price of gas has really declined recently. So what Chris Carroll did with this study is he actually modeled occurrence of sage-grouse within 5 different important time periods. We have nesting habitat, early brood rearing habitat, late brood rearing, and then for females that were not successful in nesting, we have early and late periods of time for them. And you look at the map here, the green areas are the high probability of occurrence, the red areas are the low probability. And you can see the infrastructure, especially in kind of the center area. Highway 789 that goes from Baggs, Wyoming up to Creston Junction, just west of Rollins a ways. That's kind of where this is. So what Chris did, which was different than most others have done, is he took this one step further and he developed a demographic response layer. And he used Lambda, which is an integrated parameter that represents all different life stages of sage-grouse. And when Lambda goes above 1, it indicates source habitats, or habitats where additional or excess sage-grouse are produced and survive well. When it goes below 1, it starts going towards the yellow or red areas. Those are the areas where sage-grouse go. They tend not to do very well. They definitely do not produce excess individuals. So keep that in mind. I'm going to show you some more what he did with this. This is all based on demographic data we collected from these birds all throughout the year, and a few things from the literature. So this is kind of how Chris devised his habitat categories and how he broke up his habitat into source sink habitats. You see the left there, occurrence. This is either high or low occurrence based on the occurrence modeling. Fitness for Lambda, and then you can see if an area has high occurrence and Lambda exceeds 1, then we have a selected source. On the other end, when occurrence is very low and fitness is also below 1, then we have a sink habitat. And you have to kind of keep that in mind looking at this next map. This shows right now the whole area, and we're able to predict with the occurrence model that 82% of the habitat would have been selected by sage-grouse, but there was effective avoidance in 42% of that area that would be considered high-quality selected habitat. So, basically the gas field resulted in 42% loss of habitat where birds would have used it, but are not selecting it now. And that's a really important result to think about, a gas field, and maybe in the future designing gas fields and mitigating for those impacts by avoiding certain things. And we have a whole lot of information about how sage-grouse respond to all the environmental and anthropogenic factors in this particular landscape. One of the last thing I wanted to point out was this is actually just a diagram showing the hazard rate for broods in response to surface disturbance. And so just a circle right here that Chris has within one kilometer of a location for a sage-grouse brood, there happens to be 5% surface disturbance. And this is the value that the core regions are based on for permitting oil and gas development or other things like wind energy development in these landscapes. And if you notice here, the risk rate was really low until you reached about 5%. And I don't know how this correlated so well with the Sage-Grouse executive order to sit with their guidelines, but it really did really well, which has been of really interest to the Wyoming Game and Fish Department and others that have seen these data. So just a couple of things now. Mitigation, we have these structures for how mitigation will occur. And the Atlantic Rim project area, which is this boundary outline in blue, happens to fall in both core area and then non-core area. And you see there's different stipulations placed. For Leks that are outside of core area, it's only 1/4 of a mile. With those within the core area, it happens to be 0.6 mile, giving them greater protection, even though those areas are adjacent to each other and the birds move between the Leks, and the population probably functions together pretty cohesively as well. So there are some issues with both surface disturbance and timing regulations, how those differ between the core area and outside of core area. And I have another student that's actually evaluating some of those factors as part of his PhD work. So I just close with a couple points about mitigation. Earlier mitigation was described, I thought, really well in the morning session. And you see kind of these sequential steps. We usually try to avoid impacts when possible to begin with. If we know there are going to be impacts, we try to minimize them. And lastly, like John had mentioned earlier, sometimes there is compensation for impacts that are unavoidable. Well, the wildlife information that we have from all these research studies does provide a framework to guide that. And I think some people I've heard sometimes say, oh, we just have too much research. But really, we still don't know everything, and we're especially not understanding all the mechanisms that cause this indirect impact to occur. So I just point here, the first step for reclaiming wildlife habitats is to understand mitigations. Secondly, or understand impacts. Once we understand those impacts, we can develop mitigations. And I think down the road, when we have the opportunity, eventually we're going to actually take entire landscapes and have the opportunity to actually remove the impacts that are causing wildlife to avoid certain things. And I just wanted to thank all of our contributors and supporters, both in private industry, state and federal government, and other entities that have been supportive of our work in many ways. And I'll end that and have time for questions. Thank you. Okay, the question was asked, do I have an idea about the mechanism that causes, you'll have to tell me again what you said. Okay, the nest failure around wind turbines. I'm glad you brought that up. Within 1 mile, with 1.6 kilometers of those wind turbines, there were 16 nests we found from our marked birds over 2 years, and only 4 were successful. The closest nests to the turbines were all unsuccessful. And one thing that we hypothesize is there may be higher concentrations of nest predators like ravens that occur in this area, especially because the wind turbines do create some direct impact by killing birds and bats, and they provide scavenging, dead carcasses for scavengers. So part of our continued studies, we're actually monitoring and doing point counts for ravens and raptors and see if we can model that and see if that's an effect. We kind of think that's quite possibly what's going on. I'm not sure about ground predators, but avian predators, and they both could be related to that. So we're investigating that further. It's a good question. Any other questions? That's a good question. The question was, I showed a distributional shift in elk habitat selection. Is there also a related change or decline in the elk population? And we've been monitoring that both directly with cow-calf ratios and also indirectly with body condition information that we're getting from elk organs that are harvested by hunters. And we haven't seen a decline yet with current development. With the overall numbers of elk, what we have seen though is body condition has declined, and we compare that area to another off-site reference area with fat content on hearts and kidneys, and we have seen a lower fat content on statistically lower in the Fortification Creek area, which may be an indication, but I think at the current levels of development, there's not a population change that we've seen yet. Thanks.